Okay, so in my last video, I talked a little bit about how ligands, the nature of a ligand, like the sigma only pi acceptor or pi donor, can change delta O in an octahedral complex. The same is true for a tetrahedral complex, right? Pi donors will make our splitting our delta T smaller. A pi acceptor will make it larger. So that's pretty consistent. So, but let's talk about what that actually means for us when we're looking at complexes. Like why the splitting, the DD splitting, our delta matters. So one of the reasons, so let's, as an example, let's consider an octahedral complex, D5, so 5 D electrons. So there are multiple possible configurations. So if we plot energy, here's my energy going up. And then here is my DD splitting pattern, right? Again, EG, T2G. So D5, I'm going to draw 3 different sets of EG, T2Gs. And again, keep in mind, this is delta O. So if we start filling in electrons, so lowest energy electron goes first. Here, OK, there's the Hund's rule. So 3 electrons. But now we have options. We could fill in our extra 2 electrons up here in the EG manifold. We could, when we fill 3, we could put them down here in the T2G. And we can maybe have something in between 3, 4, 5. So these all have different configurations. So they have different spin. So here, we have 5 unpaired electrons. Our S equals 5/2. Remember, the spin of electron is 1/2. If they're all the same direction, then we have 5 of them, so that's 5/2. Here, we have 3 unpaired electrons. These 2 are paired, so they cancel out, plus 1/2 minus 1/2. So this S equals 3/2. And here, this is S equals 1/2. So these complexes would be different spins. And this will also matter later for spectroscopy when we have like the different, what's called a spin state. So the reason these might happen in different situations is, again, due to the nature of our orbitals. So this energy, when we start filling electrons, OK, let's say this is 0 energy. So we're going to just kind of arbitrarily call our T2G energy 0. So it's 0 energy to start filling these 3 electrons. But then when we have to put this up here, we're paying the price of our energy cost. I'm going to call this energy cost. So for this configuration, we pay the price of 2 delta O, because we have to put 2 electrons across this energy gap. It's higher than our 0 energy. In this example, we paid the cost of 1 delta, so you think it might be lower. But at the same time, we also have this spin pairing energy. So if you remember, electrons repel each other. So by having to put 2 electrons in that same orbital, so you can see each of these is one orbital, they're degenerate. By putting 2 electrons in the same orbital, we have some electron repulsion. So we have what's called K, the spin pairing energy. So there's a price to be paid for that as well. And then here, we've put no electrons across this delta, so there's 0 delta, that we had to pay the cost of 2K. So what determines whether we have this high spin, so this is high spin because that goes 5/2. This is our low spin configuration where we start pairing electrons preferentially. It depends on whether K, our spin pairing energy, and how that matches with our delta, our DD splitting energy, also known as like kind of the ligand field stabilization energy. So that's a separate calculation that we're not going to go into for this class. OK, so basically, kind of the takeaway point is for purposes of our class, big delta means you're going to be low spin, right? That's kind of, for most cases, that's true because, right, big delta, we don't want to pay the cost of putting the electron across the gap. We'd rather pair. What changes the pairing energy K is dependent on orbital size. The smaller orbitals, you have more electron repulsion. So K is small for second and third row TMs. Okay, so if K, of course, is much smaller than delta, then we're also going to be low spin. So what this means for us is that, oh, sorry, and then one last thing. Remember, delta, keep in mind delta is small for pi donor ligands or weak sigma donors. And then this is large for pi acceptors, strong sigma donors. Okay, so these are kind of a list of these random facts for you. Well, kind of a few takeaways. So for small k's, we said that the second and third row with larger orbitals have smaller k's. So this takeaway here is that second and third row metals are almost always low spin. I know we're good to write. I'll write it here. Second and third row TMs, low spin. So that's one point that's important. So here we have kind of like some ligand binding dependencies, right? So if we want big delta, or if we have different ligands that change our delta. So one way to change delta without changing our ligands is to highly charged ions. So the more highly charged a metal is, the closer it pulls its ligand in, which means that we have bigger overlap, bigger delta. So highly charged ions, bigger delta, more likely to be, oh, sorry, that got cut off. Bigger delta, more likely to be high spin. So if we're comparing, let's say, cobalt-3 versus cobalt-2, cobalt-3 is more likely to be low spin because it's higher charge. Okay, and then lastly, our delta depends on our ligand's nature. So we said that for pi donors, they might be smaller delta, more likely to be high spin. Pi acceptors, smaller delta, or pi acceptors are bigger delta, so more likely to be low spin. So this gives us our spectrochemical series. You don't need to memorize this, but you should kind of know the general trends. So if we start comparing ligands, I'm going to kind of start out here. We have I minus. We'll have a smaller gap than bromine because it's a stronger pi donor. I minus has a higher energy filled p orbitals. And then let's see, we have sulfide, thiocyanate, say chloride. I'm obviously not listing an exhaustive list here. But just know general trends. Hydroxide, water, oh no, I'm running out of space. Okay, let's see. Acetylnitrile, pyridine, ammonia, oh, ethylene diamine, BIPI. Okay, and now we're getting into pi acceptors, triphenylphosphine, cyanide, CO. Okay, so this is an order spectrochemical series of how small band gap, I'm mixing up terms, small delta to large delta. And this is because we're starting from over here, pi donors, and then about over here to water, sigma only. And then at this very end here, we have pi acceptors. So basically, oh, sorry, that got cut off. Pi acceptors is over here. So for example, if we have you can mix some of these factors together. So if we have a first row transition metal, so we don't know that it's low spin because first row transition metals can be either high or low spin because we have small orbitals, so we might have large Ks. And then what matters is then our delta. So if we have, for example, a first row transition metal with old carbonyl ligands, we know it's a strong pi acceptor ligand, so we're going to have a big delta. So that complex should be low spin. On the other hand, if we have a first transition metal with all halide ligands, then it's more likely to be high spin because we have pi donor ligands that make a smaller delta. So these are just things to keep in mind when we're starting to predict what our electron configuration should be for different transition metal complexes.